So, we have been discussing the dynamic analysis of multi-leg articular towers. In this lecture I will show you some experimental studies carried out on this and the analytical studies carried out, so that we can understand how the response control technique can be used for controlling the response of an MLAT using a tuned mass damper. So, in the last class we discussed about the derivation of equations of motion for a primary and secondary mass system, as we see here. This is my idealized model of the tower, which has a specific stiffness and damping, which we call as K1 and C1, and of course there is a mass of the whole tower which we already computed, and we have attached a secondary mass system M2 with K2, and we said this may response which you want to control, whereas this response is dependent on this, and we found out that my equation of motion with respect to the x1 of t of x static, x1 x static as formed out with 7 variables. Then we found out some ratios and reduced this to 5 variables, and we plotted a curve which I re-show you again now, which we discussed in the last class. So, this is the plot what I have, which varies with the frequency ratio. Omega is the excitation frequency and sigma is the frequency of the fundamental system, the ratio of the fundamental system, and the y axis shows me the plot of x1 of t versus x static, because I am interested in controlling the primary response of the system here x1 of t by tuning the mass of the secondary system. In my case it is a tuned mass damper. So, I have got plots and I am plotting this for different ratios of mu, which is the mass ratio, which is the ratio of m2 over m1, which will be always less than 1, and the percentage varies from about 0.1 to 10% of that of the primary mass. The important observation what we made from this figure in the last class was that at resonance, that is when the excitation frequency omega matches with the fundamental frequency of the primary mass system sigma n, we see that the response practically comes to 0, and that is an analytical solution, because this cannot be experimentally tried, because when you excite a model or a scaled system to that of a natural or the excitation frequency to be tuned in the frequency ratio of the model, it will damage the model. So, we cannot actually study this experimentally. So, we attempted to find out different mass ratios of mu varying from 0.1 to 10%, which is the ratio of the secondary mass to the primary mass system, and the plot shows that at resonating frequency of the primary mass system, the response of x versus x static ratio becomes practically 0, whereas the peak is now shifted to the adjacent bands approximately at 0.4 and 1.1 approximately. So, you get two peaks successive to the peak of the response ratio, that is the natural frequency peak, that is resonance frequency 1. I got 2 peaks now, whereas you will see that instead of the response shooting up infinitely to a very high value, it controls at around 5. As I keep on increasing my mass ratio from 0.1%, which corresponds to this, to 10%, which corresponds to this, I am able to control my response drastically from a value ratio of around 5 to a value ratio of around 1.6. So, I am able to control. So, what attempted was is the response control of the primary system using an additional secondary mass system, which is one of the common algorithm being used for passive control technique methodology in land based structures. This was not attempted very often in offshore structures. So, which frequency or which response we are controlling here is x1 is nothing but the displacement of the deck. Of course, it is a function of the tower rotation theta, as we all understand now, but still the response control here is x1 of t, which is displacement of the deck for operational convenience of the platform. So, the figure shows that the response ratio as a function of mass ratio for different mu values, it is plotted as m here. It is seen that the effective range of observed frequency of the TMD is a narrow band, because now the width what you have here is practically narrow, okay, this very narrow band. So, it is effective only in the band width of from here to here as well as from here to here. So, the demerit what you get in this case is, instead of having a single shooter frequency value, it is having 2 response peaks shooting up adjacent to the or closer to the resonance band. So, you get 2 peaks, but of course, the peak value is controlled. Okay. So, this shows a considerable reduction in the displacement within the chosen bandwidth. Okay. Any questions here? Now, let us see how this experiment was conducted. So, based on the analytical studies carried out, we obtained different ratios of secondary mass to the primary mass system. That is why we call this as tuned mass dampers. I got to find out which mass proportion of mu will comfortably work at the bandwidth of excitation frequency of the wave for my chosen fundamental frequency sigma. Okay. For a chosen fundamental frequency sigma, which is nothing but the fundamental frequency of the primary system, for sigma n known, which mu, that is nothing but m2 versus m1, where m2 is the mass of the secondary system and m1 is the mass of the primary system, which mu can give maximum reduction. That is the optimization parameter here. Since we are tuning the mass, the whole exercise is called tuned mass, and since I am controlling the response, this is damped. So, I call this as tuned mass damper systems. Okay. This is one of the practical technique of passive control of structures. Which is being generally used for land based structures. This is now first attempted in case of offshore structures. So, based on the analytical studies carried out, we found out the different parameters affecting and tried to find out the optimum response control for the chosen configuration. Then we verified this for different ratios and confirm it from experimental investigation. It is very interesting because this study cannot be done experimentally, because I cannot tune the mass m2 versus m1 experimentally, because I may damage the primary model. Okay. So, I do it analytically, then select these ratios, because analytically I understand from the previous curve I showed you that when I attach a secondary mass to the primary system, my response is getting shifted from the resonant band. It means I am saving the primary structure, it is not resonating at all. So, now I can try with different mass ratios and try to find out the response control and verify it experimentally and see which is the feasible tuned mass which can be deployed for the specific system. So, it is problem specific, it is site specific, it is actually frequency specific. Okay. It cannot operate for larger bandwidths, it means it cannot cover a wide range of frequency for application. It has got its limitation, but within that applied limitation it is very effective. Okay. And it is an inherent system, you do not have to actually attach a separate secondary mass as we are shown in the model, analytical model. It can be inherently built. For example, ships have sloshing tanks or have buoyancy tanks which has liquid contained in it. That property can be used for tuning the response of the primary system. In that case, we call this as tuned liquid mass dampers, TLMDs. Okay. We will try to find out what is the volume effective which can be used to tune the response of the primary system. In my case, I am not using any tuned liquid mass damper, I am using a physical mass. I call this as tuned mass dampers. Okay. So, that is the experimental setup we have. It is a 4-legged articulated tower. You can see the articulation at the bottom here. There is an articulation here at the bottom, and of course, there is an articulation here at the top also, because this articulation at the top is only to reduce the bending moment at the rigid body connection between the deck and the tower, which you saw in the earlier case of single leg ATs. Okay. This was one of the geometric innovation. By providing an additional hinge at the connectivity between the tower and the deck, you can reduce the response of the rigid connection. Okay. And of course, you will realize now at this point of time of understanding, the point when I am providing the top hinge, this particular point has no wave action at all, okay, because this is very much above the mean sea level. So, there is no wave action here. Okay. So, this will not get corroded, because this is very much away from the clear head sea condition of the wave, okay, from the upper tide level or high tide levels. Okay. So, the bottom one of course is a functional characteristic, it is a structural configuration which is already present in the single leg towers also, that is nothing but a structural hinge. Okay. So, that is the experimental setup. Of course, you see a lot of instrumentation on the deck here. I will explain that very quickly, because the focus in this lecture is not to explain how the experiment was done. The focus here is how we have obtained the 2 unit mass configuration from this experiment and how the results look like. Okay, that is what we are interested in. Of course, you must understand the structural properties of the system, because that is important how the tuning was done. The attempt was made for a 1:100 scale, because the prototype is about 100 meter water depth, but the scaled model was tested in 1 meter water depth. So, 1:100 scale has been attempted. You may wonder why very intrinsic scale has not been attempted, because of the limitations in terms of attaching the mass. I am looking for a mass ratio of 0.01 onwards. Okay. If I go for a larger scale, then I will not be able to operate the upper mu ratios. If you go for a smaller scale, I will not be able to operate the lower mu ratios. So, I picked up a scale model which can accommodate my mu ratios, that is mass m to m1 ratio, which can suit my experimental setup. Okay. Of course, the density of the material, density of modulus of elasticity, all has been attempted. The size of the platform attempted here is 70 meter square, okay, which conforms to around 0.7 meter for a scale of 1:100. And of course, the free draft, the free board draft, length of the leg are all available to us. The free vibration test was conducted, and we found out that the natural period is close to around 2.7 seconds for the model. It is very important for you to remember, because I will show you at this particular point of 2.7 you are supposed to see a decrement in the response, because at resonance it has to show lesser response. That is the aim objective of this, is it not? So, we will show you how it is happening. So, 2.7, and of course, the damping ratio critical was about 2.6%. Generally, it varies from anywhere from 1.5 to 3.5 for aerodynamic structures like offshore structures, because the damping is extraordinary. This is the damping ratio of the critical of the structure. So, that is the structural property what we have for the setup, and this is actually the setup which I will show you the video now. I have got to shift the system, I will show you the video. So, you can see here there are two pictures. The left one shows you that it is at a static installed condition, and the right picture shows you that it is in the displaced condition. Okay. You will see when the mass or the secondary mass is getting displaced to its maximum, you will see the primary system is not displaced at all. Okay. There is an out of phase relationship between the second. This is exactly what we call as tuning. So, now we will show you a video how this is done, then we will go to the results. So, this is actually a collaborative study what IITM did with one of the engineering student of PhD in University of Naples in Italy. He came here to do the experiment. This is our wave flume setup. This is one of the interesting setup what we have in our department in IIT Madras. So, this video will run for a few minutes. Let us watch this, because this is interesting for us to know how the wave setup is, because for listeners who are seeing it for the first time, it is interesting for us to know how the wave was generated. It is a piston type wave maker which is 1 meter water deep flume, where I can generate current also. So, that is a piston which is activated for a specific signal, and now we are having a long time period wave. Okay. The period of the wave is very long. Let us see how the wave propagates and how it hits the model, and how the model was installed. You can see that is the length of the flume we have, and we have placed the model apart from the interference of the boundaries, and that is the model which is having there are 4 legs there. Instrumentation is done. You can see the wave probe in the beginning to check the wave height which is reaching the model. Actually, this video will show you the experimental setup and of course, the motion characteristics of the model. So, it has been online configuration has been attained by looking at the system inside, and the whole data has been acquired instantaneously as the model responds to the wave. Okay. So, this is the second thing, how actually comfortably the secondary mass can be placed in the system. So, because of the top hinge provided connecting the tower and the deck, one can easily remove the tower. Of course, for the experimental facilities. One can remove the tower easily from the deck easily from the tower and place the secondary mass. So, that is the hinged joint what we have, which is connecting the tower and the deck, and you can see on the top is a triaxial accelerometer, which is at the center marked at the CG of the deck, which is measuring the acceleration response of my deck, which I will show you subsequently. So, the deck can be easily displaced off from the tower under the installed condition. Okay, this is the installed condition actually. So, one can do this. It is not that easy when you do in the real size, because 70 meter size it is not that simple, but in the model at least it can be easily done. You can see here that is the secondary mass system where the pendulum what is picking up of a specific configuration of M2 for a specific length of L2. So, there is an arrangement below the CG of the deck which is going to hang the secondary mass. Now, the secondary mass system M2 with K2 has been connected to the system now, to the primary system, has been tightened to maintain the L2. That is a simple pendulum, which is one of the simplest way of doing a passive control, which has been attempted by earlier people in 70s and 80s for land based structures. And the deck is replaced on the hinges as ready for the experiment now. That is the response of the tower without the secondary mass system. You can see here now the deck is displaced for effective rotation of theta of the tower, which has been constantly and online acquired. So, the test has been conducted having given enough pass between the successive test matrices, so that to have a calm C state and then acquire the data. So, now let us see how this is getting modified when I attach a tuned mass damper. So, now when the system with the tuned mass damper is subjected to a wave action as generated from the piston type wave maker, as the wave approaches the model, as you see here, the tower is practically static because it is a calm C state. Now, the wave is hitting the model, the secondary mass has picked up the displacement much larger compared to the primary mass system, and at a very high response you will see slowly when the response of secondary mass becoming maximum, the primary mass has controlled down, okay, and this was operating at 2.7 seconds, and now the wave action has stopped because the period of application was only 20 seconds, and that is how it has been acquired directly. So, you can see it has been reapplied once again for the maximum displacement. You will see there are two peaks being generated now, okay. I must show you both the peaks in the deck response. You can see for a larger displacement of the secondary mass, the primary mass is almost static, okay. Earlier it was not so without the TMD. Any questions here? So, this was the experimental setup what we had, and we have seen the videos how the experiment was done. The left hand side image shows the static condition of the installed model, whereas the right hand side shows the maximum displacement of the secondary mass system at omega equals sigma when the primary system is supposed to resonate to the maximum response, okay. It is not happening here because of the advantage of secondary mass attached. It is a very simple algorithm tried, and let us see the benefits. Now, which are the focus points in dynamic point of view as far as this problem is concerned? What we are interested are the following. The targets are the following: of course, the deck response. It is not the maximum response. I am not looking at the maximum response, I am looking at the response time history. and also of course I want to know, is there any reduction in the bending moment of the tower legs. The moment I know the bending moment reduction in the tower legs, I can always work out whether there is any reduction in the stresses, bending stress of course in the legs. So, I can also protect my legs when the bending stress exceeds the permissible value in the material by the same technique. So, secondary advantage we derive. The primary advantage is functional, the secondary advantage is structural. Is that clear? It is functional because I do not want x of t be larger for operational point of view. Okay. The secondary advantage is structural, I can reduce the bending stress also in the tower. Let us see both now. Of course, I will show you the reverse order. First, I will show you the secondary benefits, then I will talk about the primary benefits. A scaled model of TMD of brass rod of different lengths of different 5, 10, 15, 18 centimeters have been tested with different mass of 50, 10, 100, 150 and 230 have been used in the study, which corresponds to the mu ratios of various percentage as we analyzed in the previous example. So, these were the different configurations and these were the percentages of the mass of TMD to prototype. It varies approximately from 1% to 4%, okay, for the present study. So, this can be achieved either having a different diameter of the member in terms of its leg of the secondary mass, can also vary the length of the pendulum, can also vary the mass of the pendulum in grams of course corresponding to so many tons. So, one may wonder that how can I suspend a 250 ton or 200 ton pendulum. Okay. I am talking about a structure whose weight is around 17,000 tons, because my percentage is only 2.85. Look at the value, do not look at the mass of the pendulum, look at the percentage of that mass of the pendulum respect to the original prototype. So, it is just 2%. Okay. This can be easily. So, it cannot be suspended as simple as you saw in the experimental setup. Okay. There are mechanisms that has got to be attempted how to handle this, but the advantages are what we are going to see now, which are important. If you look at the maximum values of bending moment, because I am interested in showing the reduction of the bending moment, I am sorry for the I think small size of the figure, but I think if you look at the same figure in a screen of a computer, I think it will be sharp enough. I am sorry because you will not see from a distance, but anyway qualitatively let us discuss it quickly. Quantitatively it is not important for you to know the numbers. Qualitatively, this is the point where I have my top hinge which is connecting the deck and the tower. This is the point where I have my bottom hinge which is connecting the tower and the foundation. So, practically I have bending moment 0 in these both spaces. These bending moments are applied, measured directly from the experiment. These are all experimental results, okay, and these are the points where they have been measured using strain gauges. The dots what you see here are the discrete points at these places where the strain was measured. From the strain the structure remains elastic, therefore, we have computed the bending stress. Okay. That is why the figure is not continuous, it is discrete, it is breaking, because these are the points where they have been measured directly from the tower. So, if you look at the maximum response in terms of bending moment, let us look at this case which talks about 200 grams TMD. This is also 200 grams TMD, where of course the wave period here and the here are different cases. Okay. So, the maximum bending moment occurs approximately at about 1/3 of the height of the tower from the top. Okay. So, as you keep on increasing the wave period for the same wave height, for example, let us say 200 grams TMD, I have the wave height as 6 centimeters in the experiment, I keep on increasing the wave period 1.3, 1.5, 1.7, of course, the bending moment in terms of kilonewton meter keeps on increasing with respect to the increase in wave height. So, qualitatively presence of secondary mass does not alter the bending moment characteristic in the tower qualitatively. Without TMD also the same scenario was notified. I will show you a comparison later. So, the bending moment will increase with the increase in wave height for or same wave height for wave periods. Okay. Qualitatively it is not, and also there is no apparent shift of the maximum bending moment because of TMD available. Okay. The location where the maximum bending moment will occur on the leg remains almost same. So, the critical cross section with and without TMD remains same. So, you are not able to shift that. Okay. What you are seeing is reduction in magnitude only. Okay, that is important. It means TMD provision or secondary mass provision in the system qualitatively is not altering the structural behavior, okay, in terms of bending moment. Let us see what happens when I change the wave heights, because the earlier case was for constant wave height. Now, I change the wave height for TMD 100 grams, 9 centimeter, 6 centimeter, 12 centimeter. Okay. I am changing the wave height. Of course, the plot is also showing different periods as well. Again, you see qualitatively the bending moment maximum occurs for all the cases at the same point, right, but there is a reduction quantitatively in the bending stress or in the bending moment. If you look at the influence of TMD on deck response, which is functionally required of x1 of t here, what we saw just then was the structural requirement. Now, we see the functional requirement. If you look at the wave height of 3 and 5 centimeters, for no TMD case, the deck response was around 1.5 and 3.2 centimeters in the model. Okay. When I attach 11.5 and 26 centimeters of long TMDs for a specific mass of 200 grams, let us say, I do not actually get a significant reduction in the deck response. It means tuning is not done for all values of wave height and wave height, it is also depending on what is the sea state. So, in this example, for a specific case, for a 3 centimeter wave height, 18 centimeter long TMD with 200 grams gave me the reduction of about 7%. When we look at 5 centimeter wave, it gives me a reduction of 9.2%, but the length of TMD is different. Okay. So, it is very difficult to exactly find out what is that TMD I must suspend to my primary mass system, which can remain effective in all ranges of wave period and wave heights. Therefore, people generally do not attempt with single mass unit dampers, they go for series of TMDs with different lengths and different weights. So, one of them will be effective in one range of wave period and wave height. So, there is a reduction of about 10% approximately. So, for a TMD of 230 mm long with 100 gram mass, the maximum reduction of the bending moment is seen. It is also seen that there is a clear reduction in the surge response of the deck for about 10%, which is advantageous. This is mainly due to out of phase response of TMD with respect to the response of the tower, which we saw in the video. So, in all the above cases, please note that the response reduction occurred at the frequency of the tower 2.7 seconds. Okay. The reduction occurred at a resonating frequency, a near resonating frequency of the tower. So, you can see a major conclusion from this kind of works. Let us say that successive peak appearing closer to the natural period of the tower shall be attributed to the decrease in strength and stiffness, because I am saying whenever the tower reaches its resonating period at which the excitation frequency matches with the frequency of the tower, there is degradation of stiffness in the tower. Okay. So, there is a shift of frequency also because of K is getting altered. So, at this time TMD assists, or the secondary mass assists the primary system for response reduction. And you will also note that the response reduction is maximum at the natural period of the tower when the TMD is attached, otherwise it is maximum without TMD, which is a simple observation in dynamic cases. The period of occurrence of the peaks as the response is not altered, as I said, qualitatively it is occurring in the same, it is not altering. Therefore, one can say that the chosen bandwidth ratio of the structural and TMD frequency is effective in controlling the response only with a chosen bandwidth, only at that bandwidth it is effective. If you go beyond the bandwidths of the two peaks which we saw, then it is not effective. So, only in these bandwidths the chosen ratios of mu will remain effective. Okay. Lower than this, and higher than this, TMD will play no role in controlling the response. Okay. So, that is very important to understand. You cannot actually plan a passive system of control mechanism for a wide range of frequency. So, generally it is an engineering attempt to try, let us try to control the response at the resonance. Okay, that is because it is expected that the response will remain maximum at near resonance case for the tower. Let us save or reduce the stresses in the tower legs and the response on the tower deck at least resonating frequency. So, we can pick up that kind of decision and design the secondary mass system to achieve this. So, the length and mass of TMD are the factors, as we saw in this case. Mass is in grams as far as the experiment is concerned, length is in centimeters. So, these are the two factors which have been tried and attempted iteratively to see which is the maximum reduction possible. However, these parameters are very important to know that they will be chosen on the basis of the geometry of the tower. So, how have we selected this 50, 100, 150 and 200 grams, or how these mu ratios of 0.1 to 10% have been selected? It all depends upon what is the mass ratio with respect to the tower, that is very important. Okay. So, they cannot be generally applied to all kinds of platforms. So, you have got to see, that is why the whole exercise is attempted to tuning the secondary mass for damping the response of the primary system. Okay, that is one of the passive technique deployed in this study. So, this has got interesting references. We have to acknowledge the authors for working on these references. Since 1984, people have been working on this. Of course, some of the studies have been borrowed from Chakrabarty and Kotta, and of course, we already referred to Jain and Datta and Kirk and Jain in earlier lectures of articular towers under waves and current. This is one of the MS thesis output which we had from IITM, which has been attempted on this particular study, and the response control has been also attempted by Sara and Marano in 2010, very recent attempt for finding out optimum design of linear two-unit mass dampers for structures with non-linear behavior. So, it has been a recent method of research where people are now focusing on response control of chaotic systems or non-linear behavior systems. So, we see here is one of the classical example applied to this problem, and so on. So, any questions? So, in the next class we will talk about recording of next class we will talk about the dynamic analysis of TLPs. We will pick up a geometric design of a TLP. We will alter the shape of TLP from square to a triangular form. We see what are the advantages and derive the mass matrix, difference matrix and damping matrices for a new innovative triangular form of TLP from research papers. We will form the equation of motion, solve the equation of motion in time domain using Newmark's beta iteration scheme, then get the results. Then one can also see, is the new geometric form stable, how to check the stability. So, we had a Matthews stability study on a triangular TLP and showed that this is much more stable on a specific degrees of freedom compared to a square TLP, whereas the cost saving of the new geometric form is more than about 40%. So, when you have a cost saving and you got a stability also and the response are much lower, this form is acceptable. That is how new geometric forms evolve in offshore engineering to go for deeper waters. We understand this mechanism in 2-3 lectures down the line, followed by which we will look up a new form which is completely non available in the literature, which has been started hinted on 1995, then experimental works have been carried out only at our place in IITM, which has been published in wide literatures, about 2-3 papers we have in journals and conferences. It is a new form. We will talk about the geometric form design, then derivations of mass, stiffness and damping matrices, again experimental analytical studies detailed conducted using star CCM and experimental studies here in wave basin. We will compare them and show the validation, then we will explain you how dynamics can be applied to these kind of practical problems. That will be the target of the second module complete lectures. Of course, we understand the principles and applications. We will move on to advanced applications of modal response characteristics and let us say stochastic response in dynamics in the third module. We will talk about applications of this. We will open up the research topic in the third module, which one can carry out forward for doing stochastic response of dynamic analysis for structures under chaotic behavior. We will talk about that in the third module, that is the target.